On Friday, we started with an overall introduction to the whole notion of quantum computing. And I hope you were paying attention because there might be a little test. We'll see. Would you please make very, very welcome for the first lecture of week 2, the first lecture of Monday, and the second lecture of her 2-lecture series, Dr. Xanthe Croot.
So welcome back. Welcome to a Monday morning of physics lectures. Today we're going to look at a really different type of quantum computer to what we looked at last time. And I'm hopeful that by the end of the lecture I kind of will have lifted the bonnet and shown you what goes on under the hood of some of the most advanced superconducting or advanced quantum computers, which happen to be based on superconductors in the world. It's not working. All right, I'm going back here. All right, so just to quickly refresh your memory on what a quantum computer is. So a quantum computer is really similar to a classical computer in that it's built from bits of information. And you can think about these bits as little switches that can be on or off, and so be in a 0 or a 1 state. But the big difference is that these systems are built from quantum objects. And we talked about how there is not just one way of building a quantum computer. There's actually a whole different range of research efforts happening globally, exploring different types of quantum systems to build quantum computers. So we talked extensively about spin qubits on Friday, but today, and so I should just remind you, this is where we encode quantum information in the spin states of electrons. So electrons act as if they are tiny little charges spinning around clockwise and anti-clockwise. And when we apply a magnetic field, we can tune the energy of an electron that's spinning clockwise and anti-clockwise. But today, we're going to look at a really different type of quantum computer. And that's one where we build the qubits from a combination of superconductors and electrical circuits. Now, electrical circuits are one of those things in physics that can be a little bit intimidating for people who haven't kind of spent a lot of time staring at them. And in fact, even if you have spent a lot of time staring at them, we're going to talk today about some circuit elements that you might not have heard before. I'm going to do my absolute best to break them down and make them simple and understandable, even if you don't have a lot of background in electrical circuits. So not to worry. And I should just mention that superconducting circuits actually are really popular. And some of the biggest players, in particular Google and IBM, have decided that superconducting circuits are the most promising way to build a quantum computer. And for a number of years, they've been going full steam ahead to try and build superconducting quantum computers. As I think I said last time, this is Joe Biden visiting IBM. They have a big center just out of New York. And looking at one of their dilution fridges that they use to cool down these superconducting circuits. Okay, so I know you've been seeing a lot of incredible science lectures and you've probably been bombarded by a huge amount of science. So rather than me doing a brief recap on what we did last time, I thought we would do a pop quiz about what we discussed on Friday. All right, so I'm going to give you a series of 5 multiple choice questions. And the first question is, what are the 2 unique quantum phenomena that distinguish quantum bits, like electron spins, from normal bits, like transistors? I can see there's a hand up, but I'm going to make your job a little easier by giving you a multiple choice question, and then we're going to do a vote. A, uncertainty, the kind of quantum phenomena where we can't tell properties like position and momentum simultaneously. Entanglement, where we can't describe a system just as its components, but we have to describe it as the complete For example, if you have two particles, you've got to describe it as the two particles. Superposition, where something like an electron spin can be spinning clockwise and anti-clockwise at the same time. And interference. All right, so hands out for A. Hands out for B. You guys are good. For C. And for D. Well done, this makes me happy. All right, so superposition and entanglement. These are all quantum phenomena, but these are the two that are really important for building quantum computers. Okay, now let's get into how we make spin qubits and how we control them. So to flip the state of a spin from a 0 to a 1, we do the following. 1, apply an oscillating electric field. 2, increase the overall magnetic field. C, warm up the experimental setup. Or D, apply an oscillating magnetic field. All right, hands up for A, B, C, D. Nice work. So that's exactly correct. If we need to flip this spin state, what we do is we come in with an oscillating magnetic field, which is perpendicular to the main magnetic field that we're applying. All right, next question. We wear special clean room suits, like these two scientists are wearing, when we're fabricating quantum chips for the following reasons. 1, they're the height of fashion. 2, they protect us from dangerous chemicals. C, they stop dust from our bodies contaminating the clean room. Or D, they shield us from X-rays. All right, who's for A?
That is true, to be fair.
Who is for B? Well done, this is a common misconception. Who's for C? And D? Excellent, that's exactly right. So I think we saw that, you know, in a meter cubed of air at room temperature, there's on the order of 30 million dust particles that are around half a micron. And so this is exactly why we wear these clean room suits, to stop dust from our body getting onto these chips where we're trying to fabricate nanometer size features. All right, question 4. Shor's algorithm is a special quantum algorithm which A, can encrypt information securely. B, can break public key cryptography by efficiently factoring large numbers into their prime factors. C, is a secret code invented by Taylor Swift. Or D, can efficiently search a database. All right, votes for A, votes for B, votes for C. Taylor Swift has done many amazing things, but I'm not sure that's one of them. And D, votes for D. Okay, great. Yeah, so Shor's algorithm is actually an algorithm that presents a problem for a lot of modern day cryptography, in that it actually can solve a problem that's really hard, that cryptography relies upon being hard. Okay, and then final question. This man, Hayek Kamali Honors, is famous for which discoveries? A, radioactivity and fission. B, the wave-like nature of electrons. C, the uncertainty principle. Or B, okay, that should be D. Or D, superconductivity and helium liquefaction. All right, who's for radioactivity and fission? The wave-like nature of electrons, uncertainty principle, and superconductivity and helium liquefaction. Great, you guys did really well. And that's really good because we're actually going to spend a lot of time today talking about superconductivity. And so to start with, who's heard of superconductivity before? Great. Who knows what it is and why it occurs? Okay, I've got one, which is great because I am going to spend the next little bit basically giving you a primer. Firstly, just in normal conductivity, and then we're going to talk about how superconductivity is different and why it occurs. Okay, but to understand what superconductivity is, we really need to take a step back And first, understand what resistance is. So I'm sure that many of you probably already have heard of what a resistor is and how it might appear and work in an electrical circuit. But basically, the resistance of a material is basically the opposition to the flow of current in that electrical circuit. So if you apply a voltage across a material that has a really large resistance, only a very small current will flow. If that material has a low resistance and you apply the same voltage, a really large current is going to flow. And many of you might know that this is represented by Ohm's law. Now, for those of you who haven't kind of spent a lot of time studying electrical circuits, you might not realise, but you probably already have a little bit of an intuition for how resistance and conductivity work. Now, before I go on, actually, I just mentioned, I've talked about resistance. Conductivity is basically the inverse of resistance. So something that has a low resistance is going to have a high conductivity or good ability to conduct electrons. And that's just represented by this. So I'm going to use resistance and conductivity to describe materials, but just remember that they're related via this expression. Okay, so you probably already have a little bit of an intuitive understanding of how resistance works. So if I was to ask you which of these two materials has the best conductivity or lowest resistance, what would you say? Copper. Excellent. If I was to ask you the same question about copper and glass, what would you say? Copper. Excellent. So you've got this idea. All right, what about copper and stainless steel? Copper, good job. Why do you say that? Excellent, yes. Actually, so there's a lot of science that goes into why copper has a higher conductivity or lower resistance than stainless steel. But they're both metals, and actually they both have quite good conductivities or low resistances, but copper is slightly better. Okay, so there are good conductors, which you kind of have an intuition for, and these are basically metals. Metals have low resistance and good conductivity. On the other hand, these materials that you identified as not having good conductivity are insulators. And so the question is, and these have high resistance and poor conductivity. So the question is what actually is the difference between these two materials that leads to one having fairly good conductivity and one having fairly bad conductivity? I can see that was a rhetorical question, but since I've got some hands up, what are your thoughts? Up the back.
Free valence electrons.
Excellent, yes, perfect. So, an insulator, basically the way that the atoms in an insulator bond is that they share electrons in covalent bonds, and there's no free electrons in the lattice floating around to conduct electricity. And so these have a high resistance because of this. In a metal, as the person up the back rightly observed, actually it's a different situation. Metals give up free electrons that can float around the lattice, and when we apply a voltage, they can move in response to that voltage and give us low resistance. Now, this is the picture that you'll find in a lot of textbooks, but it's actually not the full picture. And when you kind of get to maybe a third year condensed matter course, you start to discover that these electrons aren't little point charges moving about the lattice. What they actually do is become like waves moving through the lattice. And so if you look at this image here, you've got your lattice ions, and then basically each of these waves is a different state that the electrons can occupy as they move through the metallic lattice. So here's a question for you. And this is another question that you study in detail in a third-year condensed matter course. And that is, what happens to the resistance of a metal as we lower the temperature of that metal? Okay, who thinks the resistance is going to stay the same? Who thinks the resistance is going to go up? And who thinks the resistance is going to go down? Excellent. Why, for the people who thought it was going to go up, why do you think it will go up? Was there someone at the back? It's actually, it's not necessary. Some materials do. As you increase the temperature, if you have a semiconductor or an insulator, for example, their resistance is going to go down as you increase the temperature. But it turns out, if you have a metal, what happens as you decrease the temperature here is that the resistivity, which is just related to the resistance, goes down. Now, has anyone got any ideas about why that's so? Yep, in the front.
Because the kinetic energy of the metal lattice is lowered, and so electrons encounter less resistance as they flow through the...
Yeah, that's a great answer. So for those of you who didn't hear that, I will just kind of recap. So what happens is at high temperature, the lattice is hot and the ions are moving around. And this means that the electrons and their wave-like nature it's not like you have a completely perfect lattice for these electrons to move through as a wave. The actual ions are moving around, and what that looks like to the electrons is resistance. So, as we cool this lattice, the motion of the ions is reduced, and electrons can flow through the lattice more easily, and that continues to lower and lower temperature. You'll notice that at zero temperature, we're not actually at zero resistivity, and that's because in any metal, there's always going to be some kind of level of residual impurities that mean that your lattice isn't perfectly periodic. Okay, so that was kind of that phenomena where metals decrease their resistance as you lower the temperature. Was well known and understood in the early 1900s until this man, who we've already been introduced to, Camille Honors, was doing some experiments with mercury. Now, he had a bit of an advantage in the low temperature experiment department because he was the first person to liquefy helium. And that meant that he could do all these really interesting low temperature experiments where he probed the resistance of metals at temperatures that were lower than what they'd been probed at before. So he was in his lab measuring the resistance of mercury as a function of temperature, when suddenly he observed that rather than like a normal metal, my laser pointer, rather than this normal metal behavior, below a certain temperature, which we call the critical temperature, the resistance of this mercury suddenly dropped to zero. No resistance at all. And this is the kind of historical note in his lab book where he said mercury is practically zero. Apparently he was notorious for taking really bad notes, but he recorded this one. Okay, so turns out that this critical temperature depends on the material that you're measuring. Turns out there's a bunch of different superconductors. Mercury isn't the only one. And over the years, people have plotted the critical temperatures of different superconducting materials. So you can see that lead and niobium and different niobium alloys all superconduct. There's a lot on this plot that I'm not going to talk about. There's whole fields of research dedicated to studying materials that have critical temperatures that are kind of really high. And there's a lot of technological applications for those materials. But we're going to focus on these, which are typically the types of materials that we use when we're building superconducting quantum computers. All right, so in the next 10 minutes or so, we're going to talk about why this happens. Why do we get this sudden drop in resistivity below a certain temperature? And then also why on earth we care about this. Why is this useful for building qubits? All right, so why does this happen? Well, superconductivity was observed in 1911. And as an experimentalist, I am very familiar with the phenomena where a theorist will predict something, and then experimentalists run around for 20 years trying to observe that thing that was predicted, and doing kind of all the work in the lab to understand and see phenomena. What's really interesting about superconductivity is it's one of those phenomena that was first observed in experiment, and then actually it took another almost 50 years before people developed a theory about why this happens. And it wasn't for lack of effort. There was kind of a really continuous effort to understand this phenomena. But it wasn't until 1957 where these three gentlemen, John Bardeen, Leon Cooper, and John Schrieffer, proposed a theoretical framework to explain why the resistance of superconductors suddenly vanishes below a certain temperature. And they actually won a Nobel Prize for this work. So, what they hypothesized is that superconductivity occurs because there's an attractive interaction between electrons in the lattice. Now, on kind of first consideration, that doesn't really make sense because electrons are negatively charged and you would think that they would repel each other, not attract each other. But these men proposed this idea that as an electron moves through the lattice, it kind of attracts all the positive ions around it, just momentarily, but it attracts the positive ions and creates this region in the lattice where there's an area of extra positive charge. So then we have electron 2 moving through the lattice, and what does electron 2 see? Is that me? Oh no. What does electron 2 see? Electron 2 basically sees this region of, I've lost my laser pointer, this region of higher positive charge and is attracted to that. And so essentially the lattice mediates this attractive interaction between electrons. Now it's not a very strong interaction, which is why it doesn't occur until you kind of really suck all the energy out of the lattice and there's not energy in the environment to break that pair of electrons up. But below a certain temperature, these electrons can basically pair up and form what's called a Cooper pair. Now, in a superconductor, a Cooper pair is the fundamental unit of charge. So there's no electrons floating around by themselves. If we've done everything right, it's only Cooper pairs which are contributing to things like current. All right, so the reason why Cooper pairs exhibit zero resistance is quite complex and really in the depths of quantum theory. Let me just kind of, in a hand-wavy way, give you an idea for maybe why this occurs. So there's basically two types of particles. There's more, but for our intents and purposes, there's two. And these types of particles are bosons and fermions. And the difference between a boson and a fermion is basically the spin of the particle. And we encountered the spin of particles in the last lecture. We didn't really talk about the value of spins, but it turns out that particles like electrons and protons and neutrons have spins that basically are equal to integer multiples of a half. And we call these, well, sorry, they have half spins. And so we call these fermions. There's a different type of particle, like photons, and these have spins that can take integer values. And it turns out that in quantum mechanics, these two types of particles behave really differently. So if you have a bunch of fermions and you're trying to add them to some quantum system, they actually have to obey this rule where they can't occupy the same quantum state, and they have to kind of stack up into higher and higher energy levels as you add them to the system. And so electrons are fermions, and they have to obey that. Photons and Cooper pairs are not. A Cooper pair is a combination of two electrons, and each electron has half a spin, and so that sums to one spin, which means that the Cooper pair is not a boson anymore, it's a fermion. Sorry, it's not a fermion anymore, it's a boson. And bosons don't have to obey this kind of stacking rule. They can actually all occupy the same quantum state. And that's exactly what happens as a superconductor transitions through its critical temperature, and all the electrons pair up in Cooper pairs. Suddenly they can collapse into the same low energy state and basically move through the lattice without any resistance. And so this is kind of the physics of why materials will superconduct. Okay, so just to kind of recap that, above the critical temperature, both normal metals and superconductors have lots and lots of electrons floating around in them. Below the critical temperature though, the main charge carrier of a superconductor becomes a Cooper pair, or a pair of electrons. All right, so that's some basic physics of superconductivity. But like, why do we care about this? Why is this useful for quantum computing? And to answer that question, I'm going to go back and I'm going to touch on something that I briefly spoke about in the last lecture. So imagine I have 3 bits, and these are just normal classical transistors. And I want to encode a 111 state in these bits. So I flick all the switches to the 1 state, and it's a switch, so it stays in the 1 state. And that's great. I can do my computation with that, I can do my algorithm, and everyone's happy. One of the big challenges for quantum computing is that we actually don't stay in this state for very long if we prepare it. It's one of the big differences between classical computing and quantum computing. So if I instead switch to a quantum computer where I put 3 spins, or whatever other type of qubit I'm using, in the 1 state, it turns out that they have a real propensity to relax to the 0 state and give up the energy that they had in their 1 state. The time frame, and then we're in a 010 state, when we really wanted to be in a 111 state. The time frame on which that occurs, a 1 relaxing via the emission of some of its energy to a 0 state, is something that we call the qubit relaxation time, or the T1. And so really, we want the qubit relaxation time to be really, really long. We want it to be a long time before a qubit in the 1 state will relax to the 0. Because that means that we can get in there and we can do more logical operations, we can do bigger and more complex algorithms, and at the moment, one of the big things that limits quantum computation is the fact that many qubits, the time frame for this relaxation process can be on the order of nanoseconds to maybe, if you're lucky, a few hundred microseconds. Okay, so what has this got to do with superconductivity? Well, imagine you have a circuit and it has a resistor in it. What happens if you flow a current through that circuit? When the current flows through the resistor, it basically heats the resistor up and dissipates energy. And this is what happens. One of the kind of most obvious examples of this is a light globe. There's a current that flows through the filament. The filament has a high resistance, it heats up, and it radiates energy away. So imagine I want to store quantum information in the current of an electrical circuit. So I'm going to say that my 0 state is no current in this circuit, and my 1 state is an anti-clockwise current in this circuit. What will happen? As the current flows through the circuit, if it has a resistor, that resistor is going to dissipate energy from that current. And that current is going to get smaller and smaller until it's basically the zero state. There's no current in the circuit. And this is exactly the equivalent of this qubit relaxing from a zero state, relaxing from a 1 state to a 0 state. What would be really nice is if there was a way of having 0 resistance, which is exactly what we get in a superconductor. So if I have 0 resistance in a circuit, what I can do is I can set up a current, and I'm going to say, I'm going to put my system in the 1 state, and because there's no resistance, in theory, that current can just circulate indefinitely. So if I put my qubit in the 1 state, I set up this current, there's no resistor to dissipate that energy, and in theory, I should be able to get very, very, very long T1 or relaxation times, which would be really nice from the perspective of building a quantum computer where I can store quantum information for a long time. Okay, so this is a little bit of an oversimplification. When we make superconducting qubits, we don't actually just have a little bit of wire that we establish a current in. We have circuit elements. So let's talk about, let's try and think about building our own superconducting circuit. All right, so I'm going to task you all with the challenge of building a superconducting circuit that will make a good qubit. So we're talking about circuits, and so we have to talk about circuit elements. And this is where I don't want to lose anyone who hasn't done a lot of electrical circuits before, so I'm going to try and make it as simple as I possibly can. Okay, so the first circuit element that we've talked about at length already is the resistor. But we're dealing with a superconducting circuit, so I already know I can't use a resistor. Does anyone know of any other types of circuit elements? Capacitor and inductor. Okay, who has studied capacitors and inductors before? All right, a few of you. No worries if you haven't. A capacitor is really just a circuit element where we have one metal plate and then a gap, a vacuum gap, and then another metal plate. And what happens in a capacitor is if I put a voltage across it, I essentially build up positive charge on one side of the capacitor plate, and on the other side I build up negative charge. And what that results in is an electric field across the plates of the capacitor. So you can think of a capacitor as a circuit element which stores electric field. An inductor is really just a wire that's all looped around on itself. And when current flows through that wire, you basically establish a magnetic field in the wire. So a capacitor is a circuit element that stores electric field, and conversely, an inductor is a circuit element that stores magnetic field. We're going to talk about one more circuit element today. I just want to tell you about it now so that you're not upset when I show it later, and that's a Josephson junction. Now, a Josephson junction is a circuit element that you cannot get in a normal electrical circuit. You must have a superconducting circuit to get this circuit element. And what it is a really special type of inductor, but I will talk more about the Josephson junction when we encounter it in a few slides. Okay, but for now, let's try and make the simplest superconducting circuit that we can in order to build a qubit. So I'm going to pick the capacitor and the inductor to build my, my hopeful superconducting qubit. And so perhaps one of the simplest things I can do is just connect them so that they're kind of in a loop or in parallel with each other. And what that looks like from the fabrication perspective is just this here. Now, what you're looking at is you're looking down on the top of a chip, and that chip is really, really high purity sapphire that's about 0.5 millimeter thick, and you can see the sapphire is this grey area. In the clean rooms, we've gone and covered that chip in a superconducting metal. This in particular is tantalum. And then we've etched away the metal everywhere, except for this kind of region here, which is this circuit. So these two big pads of metal here are the capacitor, and they're going to store the electric field. And then this little wire connecting the two pads is the inductor, and that's going to store the magnetic field.
Would you like a green laser pointer? Would that make it easier?
Is that going to be clearer?
Advanced things, but at least people will see it.
Okay, thank you. Oh, that's much better. Okay, thank you. Okay, so the question is, can we make a really nice qubit out of this system? Okay, let me first tell you how this system behaves. If you go on to study physics, you will become so familiar with this system that you will be sick to death of it. But what it does, essentially, is, first of all, we have some charge that builds up on the capacitor plate, and there's an electric field that's established. But over time, that charge is going to discharge through the inductor, a current is going to flow, and it's going to establish a magnetic field. And so what happens in this system is it oscillates. And it oscillates between transferring energy from the electric field to the magnetic field and back again. And it does so at a frequency which really is just related to the size of the capacitor, which is C, and the size of the inductor, which is L. And for those of you who've done a little bit of HSC physics, really this is just the electrical equivalent of a spring. So in a spring, the spring will oscillate between storing its energy in potential energy in the spring and kinetic energy of its motion. And you can think about this as kind of the electrical equivalent, where the potential energy is the magnetic field of the inductor, and the kinetic energy is the electric field in the capacitor. But if that doesn't make any sense to you at all, that's so fine. Okay, so it turns out that this excitation is actually a photon excitation. This is kind of one photon oscillating in this resonator with a particular energy that's proportional to the frequency, which is just proportional to the size of this inductor and capacitor, as we saw before. So great, I've got a system, I can have one photon in it, I can have two photons in it, maybe I can say the one photon is my 0 state, two photons might be my 1 state. Great, I've got a qubit. Actually, there's a problem with this, and it's a bit subtle, but it basically means that this is really useless in terms of building qubits. And the reason for that is that we can't actually, the reason is that we can put more than one photon in this resonator. So if I plot the energy levels of this thing, almost as if it's like an atom, it actually has its own set of energy levels. What I find is that the energy level, this is the ground state, this is the first excited state, the second excited state, and all these energy levels have exactly the same frequency difference between them. So if I want to make a qubit, I want a 0 and a 1, and I don't want anything else participating in my qubit system. So ideally, I'd be able to shine in a photon of energy, HF, and control whether I'm in the 0 state or the 1 state. The problem with using an LC resonator as a qubit is that if I send in photons at this frequency, I might actually end up in the 2 state or the 3 state. And that makes no sense from the point of view of having a bit, which is either in a 0 or a 1. If I've got something in a state 3, that doesn't really mean anything. And so this is really problematic for using superconducting resonators like this for quantum computation. So what can we do? And the answer and the secret lies in switching out this inductor for a Josephson junction. So a Josephson junction is very much like a normal inductor, but it's got a slight non-linearity to it, which means that it creates energy levels that are quite different. So if I switch this inductor for a Josephson junction, I go from having a circuit with energy levels that are all equally spaced to a circuit with energy levels where these higher first excited states, second excited states are actually separated by less than the energy between the 0 and the 1 state. So that means I can send in photons and I can control whether I'm in the 0 or the 1 state. But these photons can't drive an excitation from 1 to 2 because this transition is not on resonance. It's not the same energy. And that means I can stay in the 0 and 1 subspace and create really nice qubits. All right, what is a Josephson junction? A Josephson junction, I've already said that it's a special circuit element that you can only get in superconductors. And so what it is basically a superconductor on one side, a superconductor on the other side, and then between them, there's a really, really thin layer, often on the order of nanometers, of insulator. Now, if this was a classical circuit element, you put an insulator between something and no current can get through. It blocks the current. But it turns out that in quantum mechanics, we can get tunneling. And that's indeed what happens. We can get Cooper pairs which kind of magically avoid this insulating barrier and can tunnel from one side of the Josephson junction to the other. And this really kind of unique quantum behavior is what gives the Josephson junction these special properties that mean we can build qubits from it. What does a Josephson junction look like? It's basically, this is a scanning electron micrograph of a Josephson junction. We basically have one layer of aluminium that we deposit, and then we oxidize it, and that aluminium will grow at maybe 2 or 3 nanometer aluminium oxide, which forms the insulator. And then we come down and we put another layer of aluminium over the top. And so the Josephson junction, this insulator between two superconductors, is this part right in the center. And that's exactly what you can see. This is a micrograph of what's called a transmon qubit, which is just this circuit here with the capacitor, similar to the resonator. But rather than having this inductor coming off to the side, I've got this tiny little Josephson junction in the center. Okay, I won't go into how we make Josephson junctions. Okay, so all of that is kind of a bit obscure. We're talking about excitations in superconducting circuits, and I kind of want to make that a little bit more concrete. So remember when we had spins, you can kind of really understand like what actually is the quantum state. The ground state is an electron spinning in one direction, which is lower energy when you align it with the magnetic field than an electron spinning in the other direction. But how is there an intuitive way that we can understand what the quantum states of this qubit actually are? And so to understand that, I'm going to paint a picture of an island. So this is our transmon qubit, which has the circuit diagram from the previous slide. And I'm basically going to say that this big chunk of metal here, which is really just one side of the capacitor, is like an island. In fact, it's a metal island. And I'm going to define the quantum states of this system as basically the number of Cooper pairs that I have on the island. Now, realistically, that's like 1 million, but I'm going to talk about it in terms of 1 or 2. But you can think, when I say 1 or 2 Cooper pairs on the island, you can think of it as 1 or 2 Cooper pairs plus 1 million, or however many there actually are. Okay, so I have my island of metal here, and I'm going to say that my 0 state is having 1 Cooper pair on the island, and my 1 state is 2 Cooper pairs on the island. Now, it turns out that this Josephson junction is a tunneling element. It allows electrons to tunnel on and off the island, and in fact allows far more interesting states than just 1 Cooper pair or 2 Cooper pairs on the island. So as I make this Josephson junction bigger and bigger, and I allow more and more tunneling, the quantum states of this island can become superpositions of Cooper pairs. The ground state might be a superposition of 1 and 2 Cooper pairs on this island, and the 1 state might be also a superposition, but with a negative sign in the middle. And this is a really quantum effect, the ability to have states that have different signs in the middle of them. If I turn on even more tunneling, I can get larger and larger numbers of Cooper pairs involved in the superposition and actually make better and better qubits. It turns out that the more number of Cooper pairs you have involved, the less sensitive this qubit is to its environment and noise. Okay, so that qubit is the qubit that's used by Google and IBM and many really big quantum computing companies. This is kind of what it looks like in a larger quantum circuit. These are the transmons here, here, and here. And everything else that's going on is just the infrastructure that we put around these transmons to control them, to measure them, and to kind of manipulate the bigger quantum circuit. This is an image from IBM. I think today is one of the biggest quantum computers that's been made. It's got 433 transmons on it. They called it Osprey. And it's got all these different layers. But the qubit layer is this second to top one here. And you can see that there's hundreds of these transmon qubits on the island. Okay, in the circuit, I should say. Okay. Okay, I'm going to go really quickly through this because I feel like I can't give this lecture without telling you about one of my other favorite types of superconducting circuits. So the transmon is something that we call a charge qubit because we define its quantum states by the amount of charge that's on this island. 1 Cooper pair or 2 Cooper pairs. But it turns out that there's another way to encode quantum information. And so we can think about this what if we get rid of the island and instead we make a circuit that has a loop in it. And this is kind of touching on this idea that we had before where we're encoding information in circuits of a loop. So what we do is we just replace the capacitor with an inductor, this circuit element that stores magnetic field. And in this circuit, current can actually circulate all the way around. So we can encode quantum information in, for example, we can say that a 0 state is current circulating in the anti-clockwise direction. Now, one very small and really cool thing about quantum mechanics is that you might be really used to charge being quantized. But in the quantum world, magnetic fields can be quantized as well. And so it turns out that this current flowing around this loop sets up a magnetic field in the center of the loop. And that magnetic field in these quantum circuits is quantized. And we call this basically 1 flux quanta is the unit of quantization of the magnetic field. So if we have current flowing the other way, we might call that the 1 state. That's going to be a flux quantum basically pointed in the other direction. And so we can have circuits where rather than having charge states, we have flux states. And we can have integer values of flux quanta in these circuits. We can define a 0 and a 1 as a clockwise and anti-clockwise circulating current, or even superpositions of these circulating currents. And this is called a fluxonium qubit, and is the other really big famous qubit that's being pursued by groups around the world. Okay, so I've given you an introduction. You kind of now know basically what you need to know about the biggest efforts in superconducting quantum computing. These are the 2 qubits that people use the most commonly. Okay, in the last maybe 5 or 10 minutes, I want to talk about some of the biggest challenges to quantum computing and address the question of, well, okay, we have some qubits, they sound like they perform well, but like why don't we already have a quantum computer that can do all the amazing things that in theory a quantum computer should be able to do? And one of the biggest challenges that we face is error. So if you kind of have your information that's encoded in 0s and 1s, what happens if when something should have been a 0, it is actually a 1, or vice versa. So if Taylor Swift wishes to send SD some information, and say she wants to send SD 101. What can happen, and what really regularly happens, is that along the way, that information is corrupted. And so that middle 0 will flip to a 1. And then SD will get the wrong information. And so in classical computing, we have to deal with this. You can't operate with these types of errors. And the way that we often do that in classical computing is we take this bit string and we implement something called repetition error correction. And it's repetition because rather than just sending 101, Taylor is going to replicate the 1 3 times, the 0 3 times, and the last 1 3 times. And she's going to send that message to SD. So imagine that one bit becomes corrupted again along the way. What SD can do is just look at this message that she's received and look at the probability that this was a 0 or a 1. And because it's less likely that 2 1s turned into 0s than 1 0 turned into a 1, she can basically decode that information and get the right message. So that's how error correction, it's one way error correction works in classical computing. Turns out that we actually can't do that in quantum computing because we can't do this process where we replicate bits. It's called the no cloning theorem. So we really have to deal with errors, and we really want qubits that don't have high error rates. And that's one of the biggest challenges that stops us building really large-scale quantum computers. So where do these errors come from? They come from things like the resistance of a circuit, which basically radiates its quantum information away. What does that resistance look like in one of these circuits? I built the whole thing, I made it superconducting, so why does it have any resistance? This is an image of some metal in a transmon qubit. And any metal has a really thin layer of oxide on the top. So when this circuit becomes superconducting, all this metal will superconduct, but there's going to be a layer of oxide at the surface that is actually quite resistive and can still dissipate that quantum information. And that's a real challenge. Another materials challenge we face is things like how clean can we make the edges of this circuit. What you're looking at here is a scanning electron micrograph of the edge of one of these capacitor pads. Ideally, we have really smooth, beautiful edges, but what actually happens is we often end up, because of the etch chemistries that we use, with really rough edges. And these types of rough edges can mean that our circuit basically dissipates energy in those edges where we don't want it to. Okay, other sources of error. Say we are trying to drive the qubit from a 0 to a 1 state with some pulse. If we accidentally don't apply that pulse for long enough, we can end up in a state that we didn't intend to end up in. And that will be an error, just that error of human control. Another really common source of error is, okay, I have some magnetic field, which is setting my qubit frequency. What if that magnetic field is changing in time? What happens to the qubit? The qubit energy actually fluctuates around. And that's really bad for being able to store sensitive quantum information in this circuit. Other times, the qubit just really likes talking to its environment. It really likes giving away photons or phonons, and it just kind of gives up its information to the environment, and it's gone from your system and you can't get it back. Other types of error, there are many types of error. One of the other ones is just that, your system is hotter than you thought it was. It takes a lot of work to get a system to 0.01 degrees above absolute zero. And if you haven't thermalized something correctly, or you don't have really good contact between your quantum chip and your dilution fridge, you can actually end up hundreds of millikelvin hotter than you think that you are. and that can really ruin your ability to control the qubit. Okay, and then finally, I'm getting really close to the end. Finally, some of the other big challenges are scaling them. These are incredibly low temperature systems. We have to pack, in theory, to do really big quantum computations, millions of qubits into these systems. This has about 50 qubits in it. And you can see that the wiring that goes from these room temperature electronics racks to the quantum computer, which will sit here at base temperature, is kind of almost as scary as some of the wiring that was used in the original computers in the 1940s. So there's kind of work being done on that actually at Sydney University. David Riley's group is doing a lot of work to see if they can integrate these room temperature electronics into the actual dilution fridge and operate them cold, so that you don't need to bring hundreds and hundreds of wires down to your very, very, very cold temperature stage. Turns out that you can't just bring infinite number of room temperature wires down to 0.01 Kelvin and stay cold. Okay, another challenge for superconducting qubits in particular is if we want to make large-scale chips with hundreds, thousands, millions of qubits on them, we really need to carefully control what frequency the qubit operates at. And the thing that sets the frequency of the qubit is how big this Josephson junction is. And unfortunately, these are tiny. These are on the order of 100 nanometers. And it can be very, very difficult to control exactly how big the Josephson junction is, and therefore control exactly what frequency your millions of qubits are going to have. People are kind of starting to figure out ways of solving this problem, first with better fabrication, but also recently, I think IBM have developed techniques where they can shine lasers at these Josephson junctions before they actually cool the superconducting chip. And that laser changes the frequency of the size of the Josephson junction, and therefore the frequency of the qubit. And so this is a really interesting way that's being investigated to kind of overcome this challenge of making qubits that have exactly the right frequency. And then finally, for systems like spin qubits, remember these electron spins in semiconductors are basically defined by these surface electrode gates, and each one of those has a voltage on it. And you need to really, really carefully tune what voltage you put on any one of those gates to be able to trap a single electron. And anyone who's worked in this field will know they will look at this device and shudder at the amount of time that it would take to tune something like this up, to get all the right voltages, such that you can have an array of 9 spin qubits. But people are working on this. They're working on ways of automating this type of process. We won't go into kind of the details of this, but this is basically the type of data that we get when we try and tune one of these things up. We measure a signal, and it tells us whether there's, this is for if you have 2 electrons. It tells you how many electrons are at each site. So this will be 1 electron on the left side, 0 electrons on the right side, etc. And so you can kind of examine this data with machine learning and teach a machine to program and tune up your quantum computer. Okay, so that brings me to the end of the talk. The big questions that I think the field is really looking at the moment are things like, what are the useful things we can do with a quantum computer before we figure out how to get these really, really, really low error rates that we'd really like? That might be many years away, but in the meantime, with the technology that we have, what can we do with a quantum computer? A lot of people kind of are realizing that the materials that we make quantum computers out of are really important for the noise that the whole system sees. And so questions of, can we explore new superconducting materials that perhaps have oxides that are less resistive or cause you to lose less energy? And could you make a qubit that performs better with one of those superconductors? People are working on, this is something that I'm particularly interested in, can you integrate many of the different forms of quantum computing technologies into one platform, so that you're not limited by any of the limitations of just one of them. You can kind of make a best of both worlds kind of situation. And then finally, can we find new areas where quantum computing might provide breakthroughs? Well, the experimentalists are in the lab working at the kind of 1 and 2 qubit level, trying to build better qubits and put more of them on the chip. The theorists are asking the question is, can we develop new algorithms that can do new and exciting things with these quantum computers of the future? Okay, so I might leave it there and open it up for questions.
Thank you, Xanthe.